could plug into the electricity if you want.
I think I have enough, but it's better to be safe. Yeah. And I use this one?
Yeah, you can, of course. Okay, you can try it.
So this is next slide.
Yeah. And here you have a laser pointer.
Well,
If you want it.
Welcome back to another session. Please remember about the feedback. Give us feedback. Actually, give the presenters feedback on what they said, what they did. There will be a prize at the end for them, so it will help if you vote for the best presentation. Also, don't forget about the lightning talks. You can propose topics, you can vote on topics. They're at 6 and 10. So if you want to participate, go for it. But for now, let me introduce Orit. She'll be talking about Ceph.
hello. Hello. Do you hear me then? This is the now. I'm sorry, this is my voice. It's a bit low, and I got a cold, so I hope if you cannot hear me, just okay, great. So I'm Orit. I'm work at Red Hat in the Ceph team. I'm currently working on the Rados Gateway, and I'm going to talk to you about it today. I will explain a bit what is Ceph, for those who don't know. Who knows here Ceph? Great. So who knows why Ceph is called Ceph? One. Yeah. So it's a family of animals in the sea. I'm not exactly sure. And that's why the Ceph symbol is an octopus. So Ceph is an open source project. It's software-defined storage, which you all heard this name a lot. Who knows what software-defined storage is? And yeah, good, some, because I'm not sure. Well, the idea is not it's just software, but it actually can fit different architectures and it fit itself to the hardware and not the hardware to the storage. Unlike many systems that actually are only software, but match specific hardware. You cannot install them everywhere. And it is written mostly in C++. It's a distributed storage system, which I believe is the way to build storage because we are talking storage is increasing all the time. And like many years ago, I was in a startup who called himself Exanet because Exa was such a huge amount of storage, and we're actually going to get there soon. I'm guessing there will be exabyte storage. Beta is quite common. It doesn't, like every good distributed system, it doesn't have a single port of failure. It was built to be massively scalable. So that means it's not for small size of nodes. It's for a big cloud. It won't perform well if you use it on 2-3 nodes. It's for a really large number of nodes, and if you're not planning to really be large, you should choose other systems. And because it was built for a really large number of nodes, you cannot expect the user to handle errors, and there will be, because when you talk about 1,000 nodes, nodes will fail, hard disk will fail, you have problems in the networks. Everything going to happen, so you need self-healing, and it fixes itself. And it allows you to have a unified storage API, so you can access it using file, block, and object. Okay, a little bit of architecture. The base of Ceph is Rados, reliable, autonomous, distributed object storage. And that's actually, it does the replication and the distribution of the data. On top of it, we have Librados, which is an API library to access Rados directly. And it has C, C++, Java, Python. And on top of it, it's the free way we access storage. So we have CephFS to access Ceph using a file system. We have RBD, which is what's commonly used in OpenStack. It's the block storage. There are two ways to use RBD. LibRBD, completely integrated into QEMU, and KRBD, which is the kernel driver. And what I'm going to talk about today is the Rados Gateway, which provide a cloud object storage like S3, like Amazon S3. So a bit about Rados. So Rados is responsible for the replication. It's an object storage, but it's not like a cloud object storage. It doesn't have RESTful API. It's flat namespace. Objects are divided into, you have pools, and objects reside in a pool. It's a solely consistent system. And you can actually define the placement algorithm depending on the topology. You can actually say that you want two copies not to reside on the same rack because you don't want two nodes on the same rack failure. And the placement algorithm is hash-based to allow really fast access, and it's called crash. And it's and actually client of Rados use the Librados to directly access the data. There's two types of node. First one, OSD, is the storage node. It's a very smart storage node. Usually in a cluster, you have large number of OSDs, between tens and 10,000. You define an OSD per disk or RAID group if you want to. Clients actually get the data from the OSDs, and it does all the replication and the self-filling itself. You have monitor nodes that you have small number of odd monitor nodes. The reason for odd number is because we need quorum in case of partition. And that monitor, all it does, it's maintain the membership of the cluster. And we use like a gossip protocol that it doesn't have to spread it to all the OSD, because when OSD interact with monitor, they actually monitor, give them the information, and the other OSD move the data all around. Clients do not access the monitor directly. So objects are divided into pools. You can say like a pool can have different replication. You can say this pool will have 3 copies, this one they have 2. You can have different placements for pools, different access control lists. In order to access the object, to know which OSD handles the object, actually, we have what we call placement group. Placement group is a group of OSDs, and they have actually the data. So if you have 3-way replication, we will have 3 OSDs in the placement group. And we use cross algorithm with the object name to actually find which placement group the object belongs to. And the cross algorithm actually is dynamic, and when you add nodes or you add OSDs, it changes the actual results in the right one. The cross is quite complex. I think we skip it. So the API Librados allows us, first of all, a single atomic object transaction. That means you can actually update metadata and attributes to an object in one operation, and it will be atomic. You also can have key value storage inside an object. You have snapshots, and it allows partial overwrite of existing data, a bit different from other object storage. And we have something like store purchases in the database. We call those Rados classes. They actually allow you to give a piece of code that will run inside the OSD when the object is written to. You can also have a watch notify events on when object is changed. So a little bit of cloud object storage. Who knows Amazon S3 or you used it? Swift, OpenStack Swift. Okay, well, I know. Those are all cloud object storage. They're also a Google compute storage or Google Cloud storage. The API are always RESTful API, HTTP based. You have users in Amazon, and in Swift you also have tenants. It actually is like a big user that allows sharing between data between different users. You authenticate to the cloud. Amazon uses the key secrets. Swift actually password. You can give access control lists to objects. That means some user can write, only some user can only read. You divide the data into buckets. It's like Swift called those containers, but they're the same. They're similar in some way to pools, but they're a bit different. I'll talk about the difference later. You have objects. Objects are like something between file and block. If block is just the data, objects also have metadata and attributes, but it's still a flat namespace. You have object in a bucket. Bucket has a name, object has a name, but they are stuff there, and that's like file system that can go on. So you have the main example is actually Swift and Google Cloud Storage. So there's a bit example how you use it. So this is S3, but Swift is quite similar, different. You add Swift and version. So it's just a simple HTTP request, and you use the HTTP header to pass the key. Not simple as it because it's a hash, but you don't put the secret in plain text. But everything goes through the HTTP protocol. So, for example, to create a bucket, you just do put of the bucket name. To get a bucket, you use get. To delete, you delete. If you create an object, the only difference is actually you give two names, and we know that it's an object and not a bucket, because we have just two levels. You can copy objects, read, and delete them. So now we're going to talk why do we need a special service and cannot access Rados directly in order to implement S3 or Swift. So first of all, Rados Gateway keeps all the state inside of the Rados cluster. So it's completely stateless. You can actually scale it out. If you have lots of clients, you can have many Rados Gateway on the same Rados cluster. Let him finish that. And all the data is kept in the Rados cluster, so even if one gateway falls, you can just spin another one, and it will read everything for the Rados cluster when it needs to. So this is today we have a quite simpler way to declare Rados class gateway. You just use Ceph deploy, and this is one line, and you can do also prepare and then activate, but it's quite basic. This one line actually runs free Rados Gateway. In order to use the gateway, you also need to create a user for S3, and this will generate automatically the secret and the key that we'll need later in order to access the cluster. This is the example for Swift. For Swift, we have sub-user because there's the tenant, but it's quite simple. So this is like the main component of Rados Gateway. The idea is to make it as layered as possible, but like always, sometimes you need to skip layers. That's the way it happens. Okay. So first of all, Rados Gateway, we want HTTP, so we need some way to actually access Rados using HTTP. So that's the front end. It actually implements HTTP. You have two ways. First way is using an external web server like Apache or Nginx. We have the fast HDI. You need to enable the fast HDI in the Apache and integrate with it. And then we have an embedded web server. It's a bit simpler, CWeb. And in that case, you don't need anything. You just run the gateway, and it will run the web server inside. We have the layer to actually translate the dialect, because all in all, the different REST API are different, but they are similar. So we don't want to duplicate code. So we have layer for each translating each dialect. And underneath, the execution layer is common, and when you create an object, it creates almost the same for Swift or for S3. In that way, it means that you can also access objects with different dialect, and create an object in S3 and actually read it with Swift. If you have users, you need the same user. Or the other way. We have a special layer we call RGW Rados. That actually maintains the data we need in Rados. And we'll go a bit more to detail about all the things we need, but we support really, really large objects. S3 limitation is 5 tera per object. So that means we need striping of the object. We need to do atomic override because cloud object storage doesn't allow to write inside an object. We need to have fast access to buckets to see which objects are in the bucket. That means we need to index the bucket. And it also runs the object class, which is like stored procedures in the OSD. We have a quota component. We have user and quota per user and quota per bucket. Authentication, it's actually more complicated because Swift and S3 and Google all do different authentications, so we need to handle each one differently and to support different authentication. And because objects are large, we want delete operation to be efficient, so they are done actually in the background, and for that we have the garbage collection that deletes all the metadata and the object in the background. So actually when you delete an object, the operation finishes immediately, but it will take time for the space to free. So we need to keep user data, bucket data, object, and ACLs per user. So why did we just did a web server and then translate maybe the REST API to command? Why do you need the Rados Gateway? So the main difference is that Rados limits the object size, it's a few giga. Objects are mutable, and they are not indexed inside the pool. And you don't have a CL per object like the cloud storage needs. So if you compare to Rados Gateway, we have really large objects, few teras. They are immutable. We need to index the bucket, so listing the content of bucket would be fast. And we need all the permissions to be flexible. So first problem is large object. How would we support really, really large objects? We want that small object access will be fast. We want to have fast access to the metadata when you list content bucket or stats on an object, but we still want to keep really, really large objects. So how do we do it? It's quite. So object is actually not one Rados object. It's several. There will always be head object. It will contain all the metadata and the attributes. Some are user also. And it's like a manifest. Swift also has a manifest for its large object. And for small object, the data can be in the head up to 0.5 mega. And Then you have the tail. It could be one or more object, or zero actually for small object, Rados object, and that's the rest of the data, the striping. Usually the stripe size is 4 mega, but you can configure it to be larger or smaller. Okay, now we have the naming. So we need to identify the object head. So it's just the bucket index, a bucket instant ID, and the object name. This is object foo. And the bucket ID is 123. We have a bucket ID because user can rename the bucket. So we cannot use the bucket name as an identifier, but we use each bucket has a unique ID, and we use that. And the tail will look quite similar. It will start with a bucket ID, but then something strange. It's a UUID, some unique ID. And then numbering means part 1, part 2, and so on. In order to actually list which objects are in the bucket, we cannot just have we need some way, something like similar to directory, a way to actually see the list of all the objects inside this bucket. We use the key value that Rados gives us. So inside the bucket index, we have a key map value of the objects. And that's why we can list buckets quite quickly. Because we allow a large number of objects, we need some time to shard the bucket index, and it actually be several objects sharded. Object creation, now because the object is not one Rados object, we need to think about the creation operation. So we actually need to create the head, create the tail object, how many we need, and to update the bucket index. It's quite similar to create a file. It has the same problem. When you create a file, you also need to update the directory. And in case of Rados, we don't have an atomic operation of several different objects. But we need to have consistency. If we, let's say, start and create the object, update the bucket index, but not create the head, then the user can list object in the bucket and see an object that doesn't exist, but will not have the object. And in other case, if we create the head first, but not update the bucket index, then the user would see it when he lists the bucket, but he can actually have an object. So we do something like two-phase commit. We first create the tail of the bucket, because that's something user cannot see. And if there will be some error, the garbage collection can clean it later. Then we add an entry to the bucket index, but it's not a full entry. We mark it as prepared. Then we write the head. And only after everything is complete and we know that the head is complete, we change the object to be complete. And then it's a regular object. This way we can handle all failure in each stage. Okay. The next part is quota. So we're talking about a distributed system. We have quota per user and quota per bucket. So that means every time a user writes an object, we need to update its quota. And it could be from any gateway in the cluster. And we have several. So if each gateway would actually update the quota itself, then we need some locking. Here comes the Rados classes. So instead of actually doing update the quota every time an object written in the gateway, it's done in the OSD. So when the objects you write to the object, it runs the code, and the code updates the quota. And then we check when we read the quota, it's already updated. And this way, we don't need to do any locking, and it's completely distributed, and it can scale. But to make things a bit complicated, we need performance, even if. So we have like user data is accessed all the time. Every time you actually do any request, you do some authentication. That means we need to see if the user has the permission to check the key secret, if it's okay. And also the bucket is always accessed every time you add an object or even read a statistic. So we have a cache layer. Each Rados gateway has its own cache. But again, we are distributed, so we need some way to invalidate the cache. Luckily, Redis has watch notify mechanism. That means that in every metadata we have in the cache, we register on it, and every time it will be updated, there will be an event, and the gateway can update it and invalidate it. Next example. So multisite. So currently we actually multisite is the what we call the Geo application of Rados Gateway. We allow to have two different geographical zones, a region. We call it regions. Two different regions be apart, and actually you can write one and see the changes in the other for disaster recovery. We call it multisite. So this is the current implementation. So a region is a geographical, logical geographic place. So you have the US East and US Europe West, for example. There are different regions because there are different Rados clusters. And in each region, you can have one or more zones. If you have, in this example, for example, you have one region that has one zone and a different region that has also one zone, and you have replication between east to west. And you can actually add a third region. So in every setup, we have one master region. This is the region that handles all the metadata. And we have in each region one master zone. This is the active zone. If you have several other zones in the same region, they will be replicated, but they will be read-only. They will be passive. Okay. Now talk about how you actually set up the setup. So you need to create a region to say if it's a master. It's all done in JSON. And you need to update this, what we call region map, and create a zone also, and update the zone map. And you need to create user for each zone and update all the zones. And we start the gateway. That's the way it's done today. It's a bit complicated. It works fine, but it's complicated. So what we're doing today is trying to simplify everything and make it like more simple commands. It's work in progress, so I can't display it yet, but it will be much simpler. So today, we have the sync agent. It's an external utility. It's written in Python, and it does actually the synchronization between the different regions. So we have, let's say, we need to sync between East 1 and East 2. So the sync agent reads the metadata from East 1, and then send the metadata to East 2. And in case of the zone, it actually tells East 2, please read the data from East 1 and synchronize. This is all that first time we have a full sync, and then it's continued to do incremental sync all the way when you have updates. In this architecture, we can only support active passive because of the way it was built. Anyone used the sync agent? No. So the sync agent today is fine, but it only supports active-passive. We actually want active-active. So an external utility cannot handle it. So we are actually writing everything again inside the gateway. This hopefully will be a tech preview in the next version in Joule, but I still don't know. So that's the problem, no active backup. So first of all, what next thing we need to add? We need multi-tenancy. A tenant is Swift has a notion of tenant. Tenant is like a big user, a super user that all the users can share the buckets between if they are the same tenants. So we add multi-tenant support. We add object expiration. That means you actually can say that if you give a date, a time to an object, and after that time, the object is deleted automatically. This way you can save space and actually remember to delete it. We're going to support AWS4, it's the S3 next version. NFS. So user requested NFS on RGW, which is not a great fit because RGW is object storage. It's not file system. So in order to implement NFS, we choose to use NFS Ganesha, which there will be a talk later today. But again, NFS Ganesha needs some API to actually talk with the gateway, and those APIs should be file-based and allow operation. Looks like file system. So we created a librGW. It's a library. We could say it's similar to librBD, so you can actually talk with the RGW directly, but it has the API that looks like file and directory API. You can do lookup. You can do like redir. It's all emulated underneath, and this way Ganesha can actually talk with librRGW to the gateway. It's one process. It's a library, so we link Ganesha together. And this way you'll have NFS by using RGW. Static website is just with domain support. Keystone v3, OpenStack is a new version. We need to integrate, so there will be Keystone v3 support. And we're going to support Swift large objects, which is Swift has a limit of few giga, if I remember, per object. So Swift large object actually, it's a way they stripped the object in order to support large objects. And we're going to support both static large objects and dynamic large objects. And we implemented multi-site. There will be a new implementation. It will be, hopefully, simpler configuration. There was a mail a few weeks ago showing an example. If everybody wants to look at the Ceph development, you can see the new API. It will be much simpler, no JSON. We will request to rename region to zone group because it's more appropriate. And it will have active-active support because it will be inside the gateway. And that's it. Any questions? Yes?
Do you have a time frame on the Keystone v3 implementation?
It will be in Joule. I hope so, yeah. Yes, it's very short time, but it should be. It's in review. And any more questions? Yeah, I have
Thanks.
Okay. Any more questions? Ceph journal, you can ask on other stuff. Ceph.
Thank you for the presentation. Could you upload me the slides, please? next speaker?
No. I just want to...
Okay. Yeah.
It doesn't. You want PDF or the
Pardon?
PDF or the pitch?
PDF it will be better. Thank you.
I just wanted to introduce myself. I'm Lara. I will be the John So I wanted to, connect places. Maybe I will sometime ask you Lara or Barbara. I already got the secret. Yeah. So maybe I just, sometime
Hello.
ask
Hi.
something.
So we are station shares here. I'm Eugene.
So
Easy?
Easy.
It's hard. Yeah, you can say. It's hard name for the foreigners. Alex. You'll take care. Oh, thank you. Great job.
Thank you.
You're absolutely.
I don't know what today.
No, it's very good job because it's very complicated. And you have short time.
I think it could be.
It's hard because a lot of people are new, some people know, some people don't know. So you have to be kind of
Everybody should know. Ceph is also because why are we not funding this?
We are. This is the thing.
Yeah, it's
This is right there. Alright. Hey, what's up, man?
If we could, before we start, we wanted to do a test for another presentation to see if the video format is okay. So after everything is set up for you, just quickly use the VGA to test.
You go ahead, test now. Test now. Sorry, I'm already addicted.
Go for it. I don't expect to have any issues, but yeah, better tested than.
Oh, sweet. Thank you.
Can you push it to that window? Well, you have to do it anyway. So it's gonna be what you see there is what you see on the screen. Okay. Again, what you see there is what you see on the screen. So it's gonna. Well, it will be kind of small here. So it's only here.
Yeah, but it is quite large range from what I heard.
So
When you will be on the stage, it should be like
small. So you would need something twice as big. I mean, just to be pleasant to the eye. Thanks. No problem. Have fun tomorrow.
You have these scarves for the questioners?
Sure.
They are free, but if you want, you can give more.
Alright. Okay.
Plenty of those.
Okay. I forgot that.
Some question, please repeat it to the recording.
Okay.
Thank you. Where are the recordings?
On YouTube. So if you go on YouTube, the Red Hat CZ, or no, Red Hat Check YouTube channel, you'll see the streams and the recordings after them.
I will do it. Thank you. I want to know where they were because they're on the web. I don't know. They're on the website, I guess.
I think there is stream.
Yeah, there's one stream. It's actually a very weird kind of stream because it's one video, one stream for all the rooms at the same time.
Oh, really?
And for example, on my mobile, I can't select through the streams. So I only see the first stream, and if I want to go to another room, I can't. If I go on,
the new technology with the changing the cameras, or
could be. It was like that last year too. So it's awesome. I mean, the idea is awesome, but actually, if you want to, so for example, if you want to share the video with somebody, you can't just go directly to the layout. So
I never used that. So
yeah.
That's weird. Alright, so I'm connected. There's one there. So, is this off? No, it should be. There we go.
That looks better?
Yeah.
Okay. So, Luis? Luis. Okay.
It's Spanish.
It's Spanish. Luis. Ah, really? There's an accent. Oh, yeah, there's an accent like that in Spanish.
Yeah. Only to the right.
Yeah. My Spanish is not that great. Okay. Anything you would like me to say in the introduction, or just hand it over to you?
Oh, no. Just hand it over.
Okay.
I got it. Sure? Yeah. I don't know. It looks like there's not many people. So.
The previous presentation was done earlier, so it should have ended now. So
Okay.
wait
till 10 minutes after?
9 more minutes. We have 9 more minutes for break, right? So we'll wait another 8 minutes at least for people to come in.
Okay. I have to move the. I'm gonna move this over here because.
Unfortunately, you can't.
Can't type.
It won't. It's not that long. I had the same problem yesterday.
Can I lift it? Is it like a.
What do you want to do?
Maybe you can lift it so I don't have to be this.
Oh, you can stand on yours. Let's see. There's another way of doing it.
Yes. Now I can just type. See? That's all.
How many left? So I just noticed something that
Yeah, I get that. Yeah, I know.